Hello everyone, Mr. Evans here with your pre-recorded live lesson for Unit 2, Lesson 6, Models versus Real Life. You have probably noticed by now that every unit has a lesson with this title. And the reason it's going over this so much is because it's trying to hammer home a certain point that I'm going to go into with a little bit more detail right now. So we're going to switch over to model cars. Okay, everyone's probably seen a model car. Maybe it's sitting on someone's shelf. Maybe you've put one together yourself. But you can buy kits of model cars, and you can get very, very detailed kits. Metal, plastic, porcelain, whatever. And some of them have thousands of little tiny parts that you painstakingly put together. And if you do it right and you do it well, you will have a tiny representation of a certain type of car. In my example here, we are using a Ford Shelby GTH. Now, if you are a good model maker and you get a very complex model, you can put together almost an identical exterior representation of a Ford Shelby GTH. It will look and feel exactly like the real thing, a real Ford Shelby GTH that you can drive. But this is still a simplified version of the car. It's not functional. If you could open up the hood here, and some of them even have like replicas of the engine, but it still won't work. You can't drive it. It's not operable. Maybe there's some that are like remote controlled cars, but it's not going to go as fast or have as much power as a real Ford Shelby GTH. So a model is a simplified version of reality. Now the complexity can vary. You can get a model car that has like 4 parts and you just kind of slap them together and that's it, and it looks okay, but it's not as complex as some other ones might be. So if you took your model Ford Shelby GTH and you scaled it up to real size so that you could actually sit in it, you could sit in it and you'd look cool in the parking lot, but it still wouldn't turn on because it's not a functional, real reflection of the real car. So scientific models are simplified versions of reality that we are constantly trying to improve. So let's switch to another example here. This is a ship in a bottle. We've probably all seen these. Now, these, again, can get very, very complex. And they're much harder to put together because you have to do it in a bottle. But people still make these. Now, if you took this ship in a bottle, and it was an identical scaled replica, and you scaled this up, you would have a functional ship. It has all the parts it needs to be a functional ship. It's got a bow, it's got a stern, it's got a bottom, mast, sails, it's got all that stuff. So if you just put a gigantor ray on this model and scaled it up, it would work. You could ride it. You could sit it in the water, the wind would grab the sails, and it would go. But even this is still not a complete functional copy of an actual built ship. It might not have the steering system. It might not have all the gears and pulleys and levers on the steering wheel to turn the sails. It would still be missing some things, even though it would be more functional. But it would still not be a perfect reflection of a real ship. So the complexity and the accuracy of models, whether those are cars or boats or scientific models, will vary. And we are always trying to put together the best model in science that reflects what is actually happening in reality. That is what a scientific model is. The goal of science, and all sciences, medicine, physics, chemistry, biology, whatever, we are trying to create models, pictures, theories, systems that can predict what will happen if you do a thing. If I do A, B will happen, then C will happen, then D. And this is what allows us to manipulate our environment, to create things, to make stuff happen. A model of a combustion engine says if I put a combustion engine together properly, when I turn the key, okay, the spark plugs are going to fire, it's going to ignite the pressurized gas in the cylinder, it's going to explode, it's going to push a piston, it's going to turn a crank, that power is going to turn to the axle, which is then going to turn my wheels, which is going to make me go. That's a model of an internal combustion engine. And it always happens, assuming your car is working right. That's always what's going to happen. We know that because science and chemistry have predicted that that's what happens in an internal combustion engine every time, assuming the car's working right. So all the stuff that you're learning, that you've been learning in biology and that you've always learned are models that people have perfected over centuries. And I'm going to take back the word perfected. Not perfected, improved. They've improved the models over the centuries, working towards perfection. Now, we will probably never get to perfection. We can only know what is working. And every now and then, someone comes along and says, hey, I've got a much better model. Throw out this old model completely. I got something way better. And look, it works. It's functional. It's predictive. It explains what's happening better than the old model. So that happens sometimes. But most of the time, people just take the existing model and tweak it around the edges, improve it, make it more functional, allow it to explain things that were not explainable before. So here's an example of a scientific model that we use just so we can kind of have a grasp of what's going on. So you've probably all seen this picture before. This is a picture of an atom. But guess what? This is a drawing of an atom. Atoms don't look like this. Atoms do not look like this at all. They don't have color. They don't have lines. They aren't circles. They don't have these cool, perfect oval-shaped orbits. They don't look like that. We have no idea what an atom looks like because they're too small for us to see. They are too small to even interact with light in a way that our eyes can interpret. So a human will never, ever directly be able to see an atom. It's like not possible for our anatomy. All we can do is come up with models like these, interpretations, drawings, whatever, that can predict what an atom is going to do. And this is like the simplest model there is of an atom. So this is the one that you're going to see in basic science courses. This just kind of gives you a basic idea of what's going on. You got your nucleus here. You've got your electrons out here. The electrons orbit the nucleus. Protons are positive. Electrons are negative. Neutrons have no charge. I mean, we've probably all heard that before. This is the most basic model of an atom you can have. And this is a very basic idea, but it doesn't look like this. We don't know what it looks like for real. Never seen it, and we can't. Now, there are more complex models of atoms. Like this is the simple one. This is also a model of an atom, but it's just much more complex. If you study chemistry in college, you will start learning about these models. You'll start learning about orbitals and the shapes of orbitals and p orbitals and electron clouds and s orbitals and probabilities of electrons existing in different parts of the atom at different times and electrons popping in and out of spaces due to quantum mechanic effects and all that kind of crazy stuff. If you get into higher end chemistry and physics, you will start learning about this and you will be able to interpret this model of an atom because it's way crazier than what you learn about in basic chemistry. But this is just an example of going from a simple model to a more complex model. And there are models that are even more complex than this one. And the more complex the model you're using and understand, the more stuff you can do with it. Using a very complex atomic model, you can predict chemistry. You can predict reactions. You can predict how electrons will flow across certain materials. And that's what you need to be using when you're in high-end science, trying to discover new applications of materials, new medicines, new pharmaceutical compounds, new fuels, whatever. So a model is a reflection of what's really going on, but it's not perfect. We're always trying to improve it. And that's what the march forward of science is. It's trying to build better models that allow us to do more stuff. So in particular to this unit, we've been talking about the carbon cycle. And this up here is the model that you've been seeing most of on the lesson. You know, you got the CO2 in the atmosphere, the plants suck it up, plants die, it goes into the soil, decomposes, the cows eat it, cows breathe it out. This is a simple model of the carbon cycle. Okay, this is a slightly more complex model of the carbon cycle. You can see there's a lot more stuff going on in here. This down here, this is a very complex model of the carbon cycle. It goes into actual numbers because there is way more stuff going on in the carbon cycle than you see either here or here. I mean, yeah, there's a lot of stuff happening here, but the carbon cycle is not this perfect little organized box where everything goes exactly where it's supposed to go. Carbon jumps all over the place in all kinds of different ways. In a bunch of ways that we don't even know yet. It reacts with other compounds in the atmosphere. It reacts with stuff in the soil. It's probably doing stuff we don't even know about right now. This model down here lays that out in a little bit more complexity. I can't even read this model. I don't know what's going on here. I'm not an environmental scientist. But if you get into environmental science, you are going to be building and using more and more complex models that give you a better reflection of reality. So all of these lessons that are talking about model versus real life is trying to hammer that idea home. That what you are learning right now is a simplified model of what's actually happening. And if you choose to go into a scientific field, you will learn about more and more complex models that actually give you the power as a scientist to do more and more complex things, to make more advanced discoveries, to build more advanced materials. So, to finish up this semester, because this is the last actual lesson of the semester, reflect on all the models that you have learned about. You have learned about DNA replication, mitosis, cellular respiration, photosynthesis, glycolysis. All of these processes that we've talked about, those are all models, and they are simple models, just to give you a foundational understanding of what's happening. And all that stuff you've learned, there is a lot more going on that has not been covered yet. But it gives you a foundation to kind of just get an idea of what's happening. If you go into the scientific field, you will go more in depth into these subjects. If you don't go into a scientific field, at least you have a very basic understanding of the process. And you know what's happening in your body, and you know what's happening in the atmosphere, and you know what's happening on an atomic level, at a rudimentary level. You're scientifically literate about those processes. You know they exist. You kind of know what's happening. And if you don't go into a scientific field, that's fine. You're scientifically literate. You are aware of it. And you can choose to learn more about it if you want to. Whether you become, something completely outside of science. Maybe you want to become an artist. Maybe you want to become some kind of technician. Maybe you want to become a carpenter or an electrician or a lineman, or maybe you want to open a business. Whatever. Being scientifically literate is important, even if your chosen field does not use any of this stuff directly. Just having an idea of it gives you a better understanding of the world. So that is models versus real life. So this is our last pre-recorded live lesson of the semester. So thanks everyone for watching. Right now it is the day before we go on Thanksgiving break, but there won't be any more pre-recorded live lessons this semester because all we have left is the apply and the cell work and stuff like that. So we will see you back for another pre-recorded live lesson next semester. So everyone have a fantastic holiday, and we will be in touch and talk to you later. Oh, the code word. Sorry. The code word today is let's see. I'm trying to think of something unique and I'm drawing the blank. Copacabana. Yeah, Copacabana. Code word's Copacabana. Great Barry Manilow song. Look it up. All right, bye. Have a great.